This video is for the sample problems for exam 3 on sequences and series. So let's go through these problems. The first one here, pretty straightforward. Write the first 4 terms in the sequence. You have n plus 1 over 3n minus 1. Usually it will say like an equals in front of that, but this one did not. That's okay. And you see what I did here? I put 1 in there for n to get the first term, a1, and put 2, put 3, put 4, and right into that formula. Pretty easy. Shouldn't be too much explanation required for that. Pretty straightforward. Let's take a look at number 2. Now, number 2 is recursive. Recursive can be a little tricky for people. Let's see if we can walk through this carefully so you can see what's going on here. A recursive sequence means any particular term of a sequence is defined as having part of one or more previous terms of the sequence being part of its equation. The most famous one is the Fibonacci sequence, where the first 2 terms are 1, and then next term is 1 plus 1 is 2, and every subsequent term adds the 2 previous terms together. Now this one's only drawing back from 1 term. So and a recursive sequence is you have to be defined at least 1 starting term. If it's using 2 terms, you'd have to be defined 2. But here it's saying a1 is 1, so that would be, if we're listing the first 5 terms, we didn't even write that there, but you see the answers all have 1. So a1 is automatically 1. An plus 1 equals an over n plus 6. So basically, each subsequent term will have the previous term plugged in to the formula. All right, so here we go. Now, here's a common mistake you have to be careful with, is that when you're trying to find a2 and we're using an plus 1, the n is 1 and not 2. So it would be 1 right here in the bottom, not 2. And then, of course, an. So basically, a2, which is a1 plus 1, will be a1 over 1 minus 6. So a1, once again, was defined as 1. So it's 1 over 1 plus 6, which is 1 over 7. So that's a2. a3 means n will be 2 because it's 2 plus 1. All right, so we'll use a2, which is 1 over 7, what we just found right here, over 2 plus 6, that ends up being 1 over 56. a4 means n equals 3, so a4 we'll use a3 over 3 plus 6. a3 is 1 over 56, divided by 3 plus 6 gives us 1 over 504. And then a5 means n equals 4, so it's a4 over 4 plus 6, so it's 1 over 504 from right here, over 4 plus 6, which is 1 over 5040. And then answer D is the correct list of the first 5 terms of that recursive sequence. All right. Here's number 3's recursive, where it uses 2 terms. It's still using the same instruction from above right here. So both these problems are using the same idea. So a1 is 1, a2 is 6, so technically to get the first 5 terms, we only need to find 3 more. So the first 2 terms are 1 and 6, that pretty much eliminates the answer C. But A, B, and D all start out with 1 and 6, so they have potential. And an plus 2 basically is an plus 1 plus an. Yeah, this is similar to the Fibonacci sequences. The only difference between this and the Fibonacci is a2 would also be a value of 1. So that means the third term will be the sum of the first 2. So if we have 1 and 6, that means 1 plus 6 will make 7. And then a4 will be the previous 2 terms added together. So now we've got 1, 6, and 7. So it's 7 plus 6, which will be 13. And A5 will be A4 plus A3. 13 plus 7 is 20. And there you go, it's answer B. Determine if the following sequence converges or diverges. Anytime you're establishing a sequence converging or diverging, you're always evaluating the limit as n goes to infinity. So it's not just some arbitrary value of n. It's always approaching infinity. In other words, we don't care what's the limit as n approaches 2 or something. Now for the factorials, you have to simplify the factorials. And you start with the one that's the larger of the two. Sometimes the larger is on top, sometimes it's on bottom, n factorials on top. And we go n times n minus 1 times n minus 2 factorial. So you cancel the n minus 2 factorials, and then you're left with nothing but n's on top, so that limit's going to go to infinity. Now here's an interesting note that on these sequences with factorials like this, on and only factorials, there's only two possible answers you can get from this. The answer had to be either diverges or converges to 0. There's no other possible answer. And it would have converged to 0 if the n's would have been left in the denominator instead of the numerator. So these other answers could never have happened. So if the n's are on bottom, it would converge to 0. So here's another factorial that shows that. So the larger factorial is on bottom. Actually, if you don't have to really write that out, basically if the larger factorial is on top, it diverges. If the larger is on bottom, it'll go to 0. But here it is sort of shown out there. n plus 3, n plus 2, n plus 1, n factorial. Those cancel. You're left with a bunch of n's on bottom, so therefore it does go to 0. But that's true every time. Larger factorial on bottom goes to 0. Larger on top diverges. Limit of the sequence. I didn't show much work here. You could technically do L'Hopital's if you want to. That would work, obviously. But then you can also look at this as the same power top and bottom. So, and we know we're going to infinity, so it's going to be 2/3. So however you want to do it, it's fine. Well, like I said, the next one, this is why you kind of want to use that method instead of L'Hopital's, because L'Hopital's would work, but you would have to take L'Hopital's rule 4 times, and it's kind of tedious. So more trouble than it's worth. When I look at this on the top and I see the largest, don't worry about the order they're in, you're just looking for the largest power. 7n to the 4th over 9n to the 4th. So they're both n to the 4th. So anytime you're going to infinity, that goes back to the basic idea of limits even before L'Hopital's rule. If you're going to infinity, you only have to care about the largest term, top and bottom. So we can eliminate everything else. And you see they're both n to the 4th, therefore it's going to go to the coefficient 7 over 9. Okay. How about this one? Let's see, the largest term on top is n. The largest term on bottom, square root of n. So when you have a larger term on top than bottom, it's, well, I just showed it was negative infinity. If you were actually evaluating the limit, which we're not in this case, back in Cal 1, you might have come up whether it was positive or negative infinity. But here, that's enough to show that it diverges. So if you flip that over, though, and you have n on bottom and square root of n on top, it would have converged to 0, because the limit would have gone to 0. Okay, this one's kind of a weird one. Now, this one diverges, but not because it goes to infinity. So there's more than one way to get diverged. Yeah, anything going to infinity will diverge for sure. But this is another example of diverge. Is the fact that these, with this negative 1 to the end, you put in 1, you're going to get 1/2. You put in 2, you're going to get 3/2. So what's happening is that sequence is just alternating terms. It just goes 1/2, 3/2, 1/2, 3/2. It's never zooming in towards one particular value. All right. So that's why that one diverges, even though it's not going to infinity. How about number 10? Now this is a good one to use L'Hopital's rule on. I like that. Now when I see a natural log and I know I can use a property, I will. So in this case, I can bring the 5 down. certainly can do it. I mean, we could have done this without doing that, but I think it makes it a little bit easier. So we can take the derivative of the top and the bottom separately. So the derivative of 5 ln of n would be 5 over n. N to the fourth would be 4n cubed. And you can drop this n. I just didn't do that, but you can drop the n down. You'll have n to the fourth on bottom 5. But anyway, that's enough to tell it goes to 0. The geometric series. Now we don't have to pay much attention to the 8 right now. 8 is going to be part of the answer. 8 is going to be your value a in the a over 1 minus r formula, which is the formula for the sum of a geometric series, a converging geometric series, with n starting at 0. That's important whether it starts at 0 or not. But anyway, what we do here is we combine the negative 1 over n with the 3 over n. You combine them together and it makes negative 1/3 to the n. And that is converging because it's between negative 1 and 1. So we're good there. So all we have to do is put 8 in here for a. And then we have 1 minus r, 8 over 1 minus r. R is negative 1/3. So 8 over 1 minus a minus 1/3 is the same thing as 8 over 4/3, which will be 6. Number 12. All right, very important here. As I wrote, n starts at 1 here. Very important. Now I've seen different ways to sort of do this. This is one way I do it. I've seen people put the value 1 in there, and I'll show you here. I'll explain that to you in a minute. But anyway, so this 5 over 9 to the n is the same thing as 5 times 1 over 9 to the n. Because remember, you can't say it's not 5 9ths to the n, because 5 is not the same as 5 to the n, but 1 is the same, 1 to the n is the same as 1, see, so, but not true for 5, so 1 to the n equals 1. So anytime you can, write, you can always write, if something over n to the bottom, like in this case 9 over n, can always be written as 1/9 to the n, because of 1 to the n being 1. So we leave the 5 there, it's going to be our a. 1/9 to the n. Now we start at 1, so here's how I do it. I look at it and go, okay, the formula a over 1 minus r right here is not going to be the right answer like it was in number 11, because that implies it's starting at 0. Okay, well that's fine. So what we can do then, so to get it to what we want, starting at 0, we'll subtract off the actual term where it equals to 0. That way, if you take, from 0 to infinity, and you subtract off the term where it's just 0, that will leave you by default 1 to infinity. So that's easy enough to put 0 in there. So you put 0 into right here. So you take 5 over 1 minus 1/9 minus 5 times 1/9 to the 0. So you get 45 over 8 minus 5, get a common denominator and all that good stuff, and you get 5 over 8. So what I was saying is you can also do this by putting 1 into this thing right here and making it 5/9, and then you let that be your a. So if you went 5 over 9 over 1 minus 1 over 9, like that, that works, because that will be 5 over 9 divided by 8 over 9, and that will give you 5/8. So that's another way that I picked up from a student one time and going, oh, I like that. Alright, so okay, let's take a look at number 13. Number 13 is going to be a telescoping series. We're going to have to do the partial fractions. The telescoping series will be 2 fractions that end up with a minus between the 2 terms. Now, unlike geometric, there's conditions on whether it converges or diverges. These telescoping series, if it's telescoping, meaning it ends up with a minus between the two fractions, it will be converging. Now, you do basic partial fraction decomp, so it shouldn't be too bad. Now, I know it shows a plus here, but we're going to have a negative. B is going to be negative. So pretty easy, clear out the denominators, and so you have 9 equals a times n plus 3 plus b to the n. You let n equal 0 to get rid of the b. That'll give me a equals 3. And then you let n equals negative 3 to get rid of the a, and that'll give me 9 equals negative 3b, so b will be negative 3. And you end up with this. Now, there's two ways you can do this. Yes, you could pull that common 3 from that numerator outside the summation. That is mathematically correct. But you must remember that you have to distribute it back when you're done. So I chose not to do it that way in this problem. But that's the thing you'd have to remember to do. Now, the idea behind this, you may recall, is that list out a few of these, and then what's going to happen is you're going to start seeing some cancellations, and then the whatever remaining terms, even they don't, you keep going on and on to show they cancel. But obviously you've got a couple terms here, that, not these particular terms, but I mean in general, that as you go farther and farther out, you're always stuck with a couple of terms, actually a third term here. You'll be stuck with 3 terms, but they don't cancel, but they go away to 0. They approach 0, limit-wise. They're going to sort of fade away to become super, super small numbers, so we just treat them as 0. So we do that, and so we ignore those, and then we look at the terms that are going to be left for sure. They aren't going anywhere. They're neither fading away. They're not canceling. We have a 3. So you know what, you put 1 in there, you get 3 over 3/4. You put 2 in here, you get 3 over 2 minus 3 over 5. You put 3 in here, you'll get 3 over 3 minus 3 over 6, so forth. But you can see that these 3 terms that I've circled are not going anywhere, while the rest of them will either cancel or fade away to 0. So all we have to do is add those 3 terms up. And it's 3 plus 3/2. Of course, 3 over 3 is 1, and we get 11 over 2. There we go. Here's another little trick for you that make this a little quicker. Is if you look at the difference in these denominators, n and n plus 3, the difference between those denominators is 3. So in other words, I'm not talking about the numerator 3. So if that would have been n and n plus 2, I would have used 2 no matter what the numerators were. That means you're going to be left with 3 terms are going to be added together. So that tells you how many terms are going to be added together, and they're always going to be the first term of each parentheses. I believe in my class notes I did one. I think there was a difference of 4, like an n and n plus 4 or something like that. So it was the first 4 terms of the parentheses that were added together. So that's kind of a nice way, shorter way to do it, or kind of check yourself if you did it this way and go, oh yeah, it's only going to be those 3 terms because the difference in the denominator is 3. So, okie doke. Partial fraction decomp. Now this one just kind of saves space here, whatever. I didn't even show the worked out decomp part there. I guess I skipped that, but obviously you can email me if you have any questions. But I got this decomposition right here. Probably should have just done it in Maple and put it there. But anyway, that's okay. I could see that my space was limited for this problem. So that's just a straight up partial fraction decomp, like the last problem. So okay, this one's kind of interesting. Now let me clarify my little rule here about n and n plus 3. That's fine. But actually it turns out different if you've got a different coefficient of n. I've discovered that, so maybe I haven't come up with a general rule for all cases. But it works for just n. So in that case, maybe you should go with just listing these out just to be on the safe side. Because what happens here, yeah, the difference in -1 and 3 is 4, but you're only left with one term here. Now this one, this one I did pull out the 3/4 just to show you the difference between not doing it and doing it. Your call, whatever works best for you. You just have to remember to multiply it back at the end. So I put in 1, and after these are gone, so yeah, I had, let's see, 4 times 1 minus 1 is 3, 7, and you put 2, you get 7 here, put in 3, you get 11, 2, you get 11 into 4n plus 3, you put 3 into here, you get 11, 3 into here, you get 15, but so look what's happening this time. Actually, only that first term is remaining. I wonder by chance, although, don't worry about this, but the difference between those is 4 and the coefficient is 4. Maybe it's 4 divided by 4 is 1. I think I'm trying to put too much into this. Actually, I wouldn't worry about that. Worst case scenario, list them out. But yeah, so that's, so if that would have been n minus 1 and n plus 3, it would have been 4 terms. The difference is 4. But maybe that 4n, obviously, well, I know it affected it, of course. It definitely did. But anyway, so you're left with that 1/3 not going anywhere. You have to remember the 3/4. So 3/4 times 1/3 is 1/4. Now the nth term test. Now the nth term test is a test that can possibly establish divergence. There is no nth term test for convergence. That's why it's basically named the nth term test for divergence. And what it says is that, and this, now here's one I was talking about earlier. So even though it's a series, it's going to use the sequence. And this rule says that if the limit of the sequence goes to any other value than 0, that means the series will diverge. So they're still two separate things, but the series rule here is using the sequence. So if it goes to anything other than 0, it diverges. So you see, without even doing those other ones, this first one, that's it. These all go to 0 right here anyway, so that limit as n goes to infinity would just be 1, n over n. 1's not 0. But we have to be careful, and I mentioned 1 over n when we first started this process. Well, 8 over n is pretty close. Pull the 8 out. But anyway, so in other words, if the limit of the sequence goes to 0, that does not mean it will converge. It just means it has a chance to converge. In other words, but if the limit does not go to 0, it's game over, diverge. So if it goes to 0, it may or may not converge. All right. This is pretty much straightforward p-series. That 10 does not affect anything. Now, when you have adding and subtracting, that's different because you can't pull numbers to the outside. But any common multiples can go outside the summation. So that 10 comes out of there. So you're looking at a p-series. And now we have to decide whether it's diverging or converging. It's all based on the exponent. So the exponent, if it's less than or equal to 1, let me add that in there just to show you. Because 1 will diverge. Put that in there. That's what makes it a little more accurate. That's good. So 3/4 means it diverges, which is correct. So it has to be greater than 1 for the p-series to converge. All right. Let's take a look at some of these. 1 over n, it's diverging p-series, also diverging integral test. Well, anything p-series is also integral, but not vice versa. All integrals aren't p-series, but all p-series could be integrated. This one here is a diverging geometric, because that's 4/3. Here's another diverging p-series. So it's this one right here, because the exponent's greater than 1. So we have a converging p-series right there. All right, so that's not too bad. Let's see what else. Let's see what we got here. That was pretty easy. Let's come on down here. Which of the following series diverges? A will converge, geometric. C is a telescoping series. It'll converge. 1 over n squared is a converging p-series. So actually you could figure it out that way. If you're confident in what the other ones do, then you would know. But this one, but then if you wanted to sort of formalize it out like I did there, you can do this. But this would clearly diverge because this 4 plus 1 over n, because if you listed out the terms, they're just going to go 3, 5, 3, 5, 3, 5, 3, 5, 3, 5, forever and ever. Never going to land on any particular value. So, and also I said space. Well, the nth term test. So I guess we can. So the nth term test means the limit, does not go to 0, but you also can add in there means, but it can go to infinity or just not exist. So it also, I guess that I should broaden my definition of nth term test based on another problem. I mean, I applied it correctly to that problem, but the moral of the story of the nth term test is the limit goes to anything. If it doesn't go to 0, it diverges. So that means not existing would certainly qualify as not going to 0. How about 19? This would actually converge by the integral test. And and the integral is really about the only one you can use here. I could see why somebody would, if they were trying to apply one, integral would be their least favorite, maybe to actually have to work it out or resolve it. It usually takes more steps. So let's take a look at this one. So it's basically U substitution. It's so it works out. Let's come down here and take a look at this. So I did a U sub of what's in here, and that's going to take care of this outside part of my du. We're just off by, a 9, so I have to make it 1 over 9 du. And the limit as b goes to infinity. I changed my limits of integration here. So u of b would be 9 over b, negative 9 over b, excuse me, it's negative 9 over x. U of 1 will be negative 9. So we basically just have cos of u du, which the antiderivative of that will be sine. We put in negative 9 of b and negative 9. And the limit for this, the key here is the limit. The sine of negative 9 radians, that's fine. That's a real number. We don't know what it means. Have to get a calculator to figure that out. But we don't care. We're just looking to see if it converges, not what it converges to. It's not that important. But the key here is what the limit does. And as b goes to infinity, that will go to 0, and sine of 0 will be 0. So there you go. So that does it, going back to the improper integrals from 8.8. So this limit going to 0, that does it. So we have a converging, technically it's 1/9 sine of 9 radians, but even if you mess that up a little bit, it's still, as long as you got the fact that it converged, that's the key. So direct comparison test, you have to be real tricky with direct comparison test. There are some series that it works great for. It's a little bit tricky in some cases, but when you need to use it, like here, it's definitely the only one you could really use. And successfully. No, limit comparison test would not work here. Yeah, there's a lot of tests that, where limit comparison tests by far is a much better way to go, because the direct can be a little bit tricky on some of the ones. Some of these weird ones, though, work perfectly for direct. So I'm going to use the fact here that we're going to compare with that 4 to the n on bottom. We're going to compare it with 1 over 4 to the n, which is 1/4 to the n. And that works out good because, the denominators are the same, so that's good. And then we can say that sine of n is always less than or equal to 1. It can equal 1, but it's always less than or equal to 1. So the direct comparison test basically says that if the larger series converges, the smaller will converge. So we know 1 over, I didn't write that down here, but 1 over 4 to the n is 1/4 to the n, which is a converging geometric. So we have it. Now, let me go ahead and mention, even though it didn't apply here, but the divergence for direct comparison test means it says if smaller series diverge, and larger series will diverge. So it only works one direction for each way there. Larger converge means smaller converge. Smaller diverge means larger diverge. So that one converges by direct comparison test with 1/4 to the n. All right, these are good. Well, of course, the answer choices are all limit comparison tests. So now what's important here, what you have to do on these problems, these are one of the favorite ones I like to put on a test, is just reduce the leading exponents. That's, first of all, that's the first, before you worry about even diverge or converge, that's the last thing you worry about, is reduce this properly. And n, I wrote it down here, okay, excuse me. Take a look at what I already did there. So I took the square root of n over n to the 3/2, because the square root of n is n to the 1/2. That would reduce into 1 over n. So basically, I'm looking for something with 1 over n. So that takes these out. And now, does it converge or diverge? Now, the thing about these limit comparison tests, I didn't actually work this out, but I'll go ahead and tell you this. As long as you compare it, maybe I should have worked it out just to show you, but if you work it out, you'll get a finite and positive number there. This is going to work out okay. But these kind of problems where they're all kind of, polynomial terms, that wouldn't have worked for that last problem with sine. But here, as long as you pick the right thing to compare it with, the limit comparison test will work. Because if you do the limit of this original one compared with this one, you'll either get 8 over 4 or you'll get 4 over 8, depending on which one you put the top or the bottom. Well, whether you get 2 or 1/2, that's a finite and positive number, so that works. So it'll work either way. But now you have to decide, so the key is whether it converges or diverges is what does the series do that you're testing it with. Well, 1 over n is a diverging p-series. And since our limit, if we did the limit, like I said, would have been either 8 over 4 or 4 over 8, depending which one I put on top, put on bottom. So you might want to try that if you want to for practice. It would have been valid, because if you don't pick the right thing to compare it with, you're going to get an invalid result, like either 0 or infinity. That tells you nothing. But anyway, 1 over n's diverging p-series, that means the one we're comparing. So the original one will diverge because we compared it with a diverging one. So it diverges by a limit comparison test with 1 over n. All right, those are a lot of fun. This is an alternating series. Just have to worry about whether it converges or diverges. I like to keep these pretty basic. Now, of course, we'll talk about the absolute or conditional convergence, which is a little bit trickier. But alternating series test is pretty straightforward. It means you take this, look at the sequence without the negative. Don't worry about the negative 1 there. You look at the sequence. That's got to go to 0. All right, so that checks. And then you're looking to see that it's decreasing. Actually, a series, I think I have one in my notes maybe where it increased for a couple terms, then started increasing on and on, decreasing forever after that. So it was okay. So it could actually start out increasing a couple of terms. But I just put in a couple numbers to show it was quickly decreasing. I mean, that's good enough. I'm not looking to try to trick anybody with this. But another way mathematically you could look at this is if you took the derivative of this function right here, you would see that it was negative for those positive values. So negative would mean that it's decreasing for all positive numbers. So anyway, but that's fine. You don't need to do that. It's almost like very rarely have I seen one, make it through the first test and fail the second part of that. So, but it didn't hurt to take a quick peek at it though to see what. Alrighty, let's take a look at this next one. Here's another one. You got to compare the exponents. Got to be real careful with this one. You don't have to worry about the coefficients here. Just look at the powers. So it's n over n to the 5 halves because of the square root. So n over n to the 5 halves is 1 over n to the 3 halves. So you see it's very important that you get that. First two important things is that you get that right, to make sure you don't pick this or this. Now the next important step is to get it down to the final answer by determining whether it converges or diverges, and it's going to be based on what does 1 over n to the 3 halves do. 1 over n to the 3 halves is a converging p-series. Therefore, our series up here, the original series, will converge by the limit comparison test with that p-series 1 over n to the 3 halves. All right, how about this? Absolutely, conditionally. Looks like, well, you know what? This should say conditionally up here. Absolutely converges or diverges. That's okay. That's not good. Let me see if I can. Didn't notice that, but okay. All right, let's shrink that down. I'm sure it probably wasn't too disturbing because you see the answers. I'll just leave it right there. That's fine. And just show you a quick boop. And this goes right in there for that. So, all right. But the answers show the phrase conditionally, converges conditionally. So, there's a couple ways you go about this, but let's just explain the way that I did this. I don't think one's necessarily better than the other. I've, sort of informally surveyed students, in a face-to-face class when I'm teaching this to see what they think. And I think this seems to be the most popular way to do it. So the first thing we do is if we do the alternating series test, and if we get diverges for the alternating series test, that means the problem's over. We just pick diverge as the answer. We're finished. But if we get converges by AST, what that does is that eliminates diverge as the answer, but it does leave us with the possibility of getting conditionally or absolute converge. So we have to go one more step. Let's go with that. So let's see what I've done here. All right, took the limit of it. Without the negative there, it goes to 0. Check. I didn't even write out any terms. I just basically checked that off. I might have looked at a couple in my head or whatever, but like I said, it's I can't imagine you would have one on a test. In fact, I know you wouldn't, where it passed the first part of this and failed the second. So we've effectively eliminated diverge from this problem. As you see, I wrote right there, eliminates diverges. Now we have to analyze the series. You look at it without the negative 1. and decide what it's doing. Kind of squeeze this in because I don't have enough room here, but so you see you have a no ends on top and an n to the 1/4 on bottom. So we would do an LCT with 1 over n to the 1/4. And that's the right thing to compare it with. So, but it would diverge because 1 over n to the 1/4 is a diverging p-series. So that makes it diverge. Okay. So let's see what we got here. Now, since the series, now that this is being written in this form, when I wrote this one, I mean the original series with the negative, that converged, but the absolute value, meaning getting rid of the negative, diverged. That's called converged conditionally. So what that phrase basically means, which you don't have to worry about what it means that much, but I'll go ahead and tell you anyway. What that converged conditionally means is that it's saying that this series has to have the negative 1 to the n to converge, meaning it did not converge without it with just the 1 itself. Absolute convergence, which I'm sure we probably have one of those coming up, maybe, or yeah. Absolute converges means it would converge with the negative 1 or without the negative 1. Either way. But this one's conditional because it had to have the negative 1. This concept can be a little tricky for students, I realize that. So, let's take a look at this one. So the negative 1 to the n, of course, makes it alternating. And if you did the alternating series test, that limit's going to go to 0, 2/3 to the n, and then it would, the terms would decrease. So it converges by AST. Then if you take the absolute value, so without the negative 1, it's a converging geometric. So it would converge absolutely with or without the negative. I guess another way to look at this particular problem, not all of them are going to work this way, but it's still correct. Absolute converges with or without the negative, but without even doing the alternating series test. Just this one happens to work out this way. So this is a general rule. But you see, if you combine, since they're both to the n power, you could actually combine them and make it negative 2/3 to the n, which is still a converging geometric. So that's another way it converges with and without the negative 1. So that's okay. Maybe I don't worry about that. I would just kind of stick with this process right over here, because that was just a rare fluke that did that. So how about this next one, number 26? Okay, you do the alternating series test, game over, because that goes to infinity. It did not go to 0. Anything other than 0 diverges, so it's diverges. You don't have to even go to the next step. That's it. So that was quick. How about number 27? We got the ratio test. Ratios when you're kind of combining stuff like, weird stuff. Factorial is a good clue. Not like the sequences. Remember, we talked about the difference. There was not factorial sequences, but factorial series are usually ratio tests. I mean, I don't want to say 100% of the time, but I'm going to say 99.9. I can't think of one that isn't, but there could be. All right, ratio test. So you put in the n plus 1. So remember, this is my shortcut way of doing it in the notes, but technically it's a n to the plus 1 over a to the n. But to make it quicker in the notes, when you're dividing by a to the n, you're essentially multiplying by a reciprocal. These are fractions. So when you divide it, so what I do is I just skip to the next step here. So I put in n plus 1 right here. Actually, it wouldn't have affected anything in this answer, but keep in mind that it's 5 times n plus 1, so it's 5n plus 5, not 5n plus 1. That wouldn't have affected anything here, but still, I figure we might as well do it right. And then on this side, so basically it's like dividing by the original terms and then flipping it over. So you see e to the 5 over n now on top, n factorials on bottom. So n plus 1 factorial is the same thing as n plus 1 times n factorial, which I didn't write that down, but I just said it. So it leaves an n plus 1 on top, and over an e to the 5th, so clear, that's just a number on the bottom. We're not e to the n, e to the 5th, so it's just a number, so that goes to infinity, so it diverges. It's got to go to something less than 1. Let's see, 8 to the n over n factorial. You have 8, put in n plus 1, so you have 8 to the n plus 1 over n plus 1 factorial. And then flip this one over, you're just dividing by it, so we're multiplying it by its reciprocal. So it's n factorial over 8 to the n. And that leaves an 8 on top and n plus 1 on bottom. Eight over n plus 1, limit as n goes to infinity of 8 over n plus 1 will equal 0. And 0 is less than 1, so we have converges by the ratio test. Here's just a little helpful hint for you. One thing, the ratio test and the limit comparison test are not compatible. They don't work at the same time. So anything that you're applying, if you have problems that involve, which this test will, and I believe because one of your quizzes does this, and the test will do it too, maybe have questions where, which of the following work? Maybe it might say, I'm just using this for an example, but limit comparison test, ratio test, it might say both limit comparison and ratio, so you have to know, even though none of these questions are asking that, you need to be able to know how to do that, know how to answer questions that involve, if more than one apply. But ratio and limit comparison test never work together, so that they would never. You may recall earlier, I mentioned earlier about p-series also being integral test working. So in other words, if something was a p-series and one of the answer choices says both p-series and integral would work, you would want to include both of those because that would work. So you have to be able to use the idea. So I think so. There was a quiz that I don't think none of these are doing it, but we're just working with each of the. Let me just double check. Yeah, we're just working with just each of the individual series types here, and I'm not asking any of those questions where they, more than one way. But be aware of that. Okay, pretty easy ratio test here. N plus 1 to the 8th over 8 to the n plus 1. Flip it over, 8 to the n over n to the 8th, and you'll have 8 on bottom, because you have 8, because remember that's the same thing as saying 8 to the n times 8 to the 1. Heck, you could even put a number in there for n if you wanted to check, and you would see it would be 1 over 8. You could do it that way. Now let me mention what's going on here with this one. These are not canceling because they're algebraically equivalent. That's not true. N plus 1 to the 8th does not equal n to the 8th, but the limit as n goes to infinity would be the same. Because if you expanded all this out, which we're not going to do, but all we need is the first term, we have n to the 8th and we have n to the 8th here. So no matter, the smaller terms won't matter as you're going to infinity. So the n to the 8th would just be 1. So we have, that's going to go to 1. That's why that cancels, not because it's an algebra reason. That would be wrong. But limit as n goes to infinity, it's not wrong. Root test is pretty easy. Root and geometric work together. Well, let me rephrase that. All geometrics are roots, but not vice versa, because this is not geometric right here. But if it's actually a geometric works with, geometric is also ratio and root. And integral, technically. just to make it, try not to confuse you here, but yeah, that would also, you can also integrate the ones that are geometric. You don't have to actually do the integral, but there's a rule back when you learn like logarithmic integration where you can integrate a to the n. Since I'm doing this freehand, I'll just do a to the x instead of n. So yeah, that's what geometric basically is. So this integral is 1 over ln of a to the x. Yeah, so actually geometrics have, if they're geometric, they have 4 ways you can actually come up with the answer. But let me clarify what I said here, though, is, all roots are not geometric, but all geometrics are roots. But anyway, the root test is easy. Let me go back to what I was saying. You're just taking the nth root of that n, so you're just killing the nth powers going away, and then you're just evaluating the limit as n goes to infinity. It has the same convergence result as the ratio test, meaning if it's less than 1, it will converge. One or more than 1 diverge. 1 and 1 itself is inconclusive. You get exactly 1. Okie doke. So you're just getting rid of that nth power and evaluating the limit of the inside as it goes to infinity. ln of n over 2n minus 9. And the derivative is L'Hopital's rule here. The derivative of ln of n is 1 over n. The derivative of the bottom is 2, so 1 over n over 2 goes to 0. So we absolutely have convergence here by the root test. All right, let's look at 31. Take the nth root of that, so it gets rid of the n. Take the limit of the inside, which will be 3n squared over n squared. You don't need to do L'Hopital's rule 2 times. You can just look at the fact they have matching powers, and it'll be 3 over 1 makes it 3. 3 greater than 1 diverges by the root test. Taylor polynomials, pretty easy. Plug and chug, there's the formula. Just be careful when you're taking the derivatives. I don't like these derivatives get too ugly, but I like ease. Sine and cosines are good. Yeah, I don't want anything that like turns into like product and quotient rules and gets too out of hand, complicated wise. So, all right, so we start with either negative 4x. We're doing a 3rd degree polynomial, so we have to take 3 derivatives. And we have, so every time you use the chain rule, every time we take the derivative, all we're doing is multiplying by negative 4. We get a negative 4. Negative 4 times negative 4 is 16. Times negative 4 is negative 64. And f of 0, you got to put in the zeros, f0, f prime 0, double prime, triple prime to get your constants here. You'll get negative 1. So all those e to the 0 is going to be 1, so you're just dealing with the coefficients here. So obviously you'll have the Taylor polynomial formula on your formula sheet. Plug it right in there. And of course 2 factorial is 2, 3 factorial, 3 times 2 times 1 is 6. So I don't know on an exam if these are going to be like reduced fractions or not. So, but that obviously that's not too complicated if you have to reduce them. But that's why I left it unreduced, because I knew that they weren't reduced here. So pretty straightforward. So it's definitely answer B here. Here's another one, natural log. Take 3 derivatives, 1 over x, which is basically x to negative 1. I wouldn't do a quotient rule. You'll get negative 1 over x squared, and you'll get 2 over x cubed. Put in 7 in all those. So you see those all go in front. So we're centered at c equals 7, so that means you're going to have x minus 7, x minus 7 squared, x minus 7 cubed. And your 2, of course, that's your 2 factorial. Your 3 factorial, 6. And so we have a 1 over 7 right here. ln of 7 is the first term right there. 1 over 7, x minus 7. And then 1/49th x minus 7 squared over 2, which will turn into over 98. And then this one, now this one they did reduce. Because what happens is 2 over 6 is 1 over 3. 3 times 343 is 1029. So we have to be very careful here, especially between answers A and B, of course. But watch, they're all, watch your pluses and minuses there, and you'll be fine. Well, that's definitely answer A. Radius of convergence. Radius of convergence, we have to do, this is power series now we're talking about. Now, power series always converge. So it's not a matter of them diverging. They always converge, but they may only converge at one, at a minimum, they'll converge at a single number. That's the minimum. So you do the ratio test. Let's see what you're left with. Because there's 3 things that can happen, basically. And I might not be saying these in the same order of my notes, so that's okay. You converge at a single point. You converge in some sort of real number interval, like say between 1 and 5, or you converge for all real numbers. So I put in n plus 1 everywhere. We have this right here times the reciprocal of the original. Start simplifying. Now this is based on what I told you earlier. Remember about this, they don't cancel algebraically, but their limit would equal 1. That's what's going on right here. Now these two, the x minus 8, we'll leave an x minus 8 on top. And then the 2 with the n plus 1 on bottom, we'll leave a 2 on bottom. So you're left with x minus 8 over 2. So whenever the n's go away, you're going to have an interval of convergence of real numbers. So you're either going to have this situation, or you're going to have n's on top, or you're going to have n's on bottom. The x isn't going anywhere. So what we do is set this x minus 8 over 2 less than or equal to 1. Move the 2 over. And once you have that denominator cleared, that means that 2 will be the radius of convergence. But if you worked it out further, the radius of convergence is basically the distance from the center to either endpoint. But like I said, you start out with 1. If there's no denominator here, the radius will be 1. As soon as you move that up, that makes it 2. But if you were to complete this, which I believe it's doing in the next problem, yeah, I'll just do this right now. If you work that out, you're going to end up with x minus 8 and then 2 here and then negative 2 here. Going back to algebra, how you evaluate these absolute value inequalities. Well, you add 8 to both sides, you're going to get 6 and 10. There's 2 ways you can do it. The radius would be 2, because you can say the difference from 8 to either 6 or 10. You can also look at it as the distance between 6 and 10 divided by 2. That distance would be 4, so you can do it that way, or the first way that I did it. But either way, the radius of convergence is definitely 2. So let's take a look at 34, which is going to actually come up with that interval. So you see, now I split that up like I was writing on the other page. I get 6 to 10. Now these are the most challenging of the 3, just for the fact is you have to test the endpoints. Because there are 4 possible, once you get this interval, there are 4 possible answers you can get. Either they're equal at both ends, they're not equal at both ends, or the lower end can be equal and the other one not, and vice versa. You just have to test each one and see. And to test, what you do is you plug the endpoints in from the x, and then you look at the series that's left, and then you use the other techniques in this chapter, whatever you think applies, to determine whether or not it converges or diverges. So if it converges, that means we're going to include that number in the interval. If it diverges, that means we would use an open, we would use this symbol if it doesn't converge. Looks like these are, of course, you could have a problem on a test that has, brackets instead of, obviously, so I would assume that Cal 2 student would know how the brackets and the parentheses work for inequalities. Looks like theta. Well, anyway, that's not what it's supposed to be. It's 10. Yeah, this one's closed. But let me explain why it's closed. So it looked like that. But obviously, if one end was open, you'd have a parentheses. All right. We'll test it. I'll put 6 in there. I put 6 in there. I get, and I didn't show a lot of work here, I guess probably because of space, but I'll go and explain it now. 6 minus 8 will give you negative 2 to the n. So actually, negative 2 to the n divided by 2 to the n would just be negative 1 to the n. So they have the same exponent. You're taking negative 2 divided by 2, and you have negative 1 over negative 1 to the n over n cubed. And that's a converging alternating series test. Now, for these, you don't have to test conditional or absolute convergence. The only time you have to do that is when it asks for it in the problem. Otherwise, perfect. So it's converged here. Now, when I put 10 in there, I get 10 minus 8, 2 to the n divided by 2 to the n. That's just 1. So then the n's go away completely. So 1 over n cubed, converging p series. So this one happened to work out where it's, oh, there, okay, there. I wrote the brackets up there. I forgot to look here and see I had them to show you, but closed at both ends. All right, here's a radius of convergence. And power for this power series. And ratio test applies. So we have x minus 3 to the n plus 1 over 2 times n plus 1 plus 5. Flip over the original, 2n plus 5 over x minus 3 to the n. So this all cancels from a limit standpoint. It cancels a 2n and a 2n. And we're left with x minus 3 right here. Absolute value of x minus 3. So that makes the radius of convergence 1. Because it's x minus 3, absolute value less than 1. In other words, there was no denominator number to bring up and over, like to multiply by. So it's just 1. Like I said, you could expand that out. But anyway, we'll do that in the next step. So that's our radius. So we're using that same work. We're expanding it. So the absolute value inequality would translate to this kind of inequality with negative 1 and positive 1. Add 3 everywhere. So it becomes 2 to 4. So like I was saying earlier, r is also 1 because 3 is x minus 3 means 3 is the center. So the distance between 3 to either end would be 1. So we have to test. Plug in 2. You get negative 1 to the n over 2n plus 5. That would be converges by alternating series test. FYI, not needed for this problem, but if it's something you wanted to try to think about and solve, it would be conditionally convergent. But that's not critical here. If you put in 4, you get 1 to the n, which is just 1, over 2n plus 5. And you could do a limit comparison test, or actually integral test would work. So it's just obviously, if more than one works, I don't have to show them all, but I like the LCT for this one, though, because that would be the easiest. Just do it with 1 over n. And easy to show that will diverge. Well, it's because the limit exists, and then and what you're testing with is diverging, so that does it. Now, direct comparison test, would that have worked here also? That's one you got to be careful with, because you have to be careful of it not applying. Let's say if you used 1 over 2 to the n, no, because that would not work, because 1 over 2 to the n is a larger series, and you can't say larger diverge doesn't mean smaller diverge, even though it does. Direct comparison test just wouldn't work here, but integral would. Radius of convergence, so let's see what happens here. Okay, so x minus 4 to the n plus 1 over 3 times n plus 1 factorial. And flip over the original to have 3n plus 1. 3n factorial over x minus 4 to the n. And then this is actually 3n plus 3 factorial right here. So it's 3n plus 3, 3n plus 2, 3n plus 1, x on top. So when all the n's are at the bottom, remember this, the limit, the x is not affected by n here. It says n goes to infinity. So the x doesn't matter. That's going to go to 0 because all those n's on the bottom. Actually, even one n on the bottom is enough to make that go to 0. So it's going to go to 0, and when that happens, you've got converges for all x. So that means your interval of convergence is negative infinity to infinity, and the radius would just be infinity. Okay, so that's what the next one is taking on, is just using that other. So there really wasn't much work here. Once the radius of convergence is infinity, that means the interval is all real numbers. Okay. Now the next one, which actually this is going to be the third case of the three, you either get rid of the n's on bottom, which we just had in the last problem, and now you end up with n times x. I'll just kind of skip this part right here. Come over here. We have n times x. You might think, hey, infinity is going to go to infinity. It's going to diverge. That's not true, because like I said earlier, there's at a minimum, there's always one number that can make this thing converge at a minimum. Well, what that number has to be, the only way this can possibly converge, is if you pick the value for x that will make this 0. Therefore, all of that will turn to 0, and you'll have convergence because it will be less than 1. By the ratio test, 0 will be less than 1. Anything other than 3 you put in here, that's going to go to infinity and it'll diverge. So it converges only at x equals 3. So when you converge only at a single point, that means the radius of convergence is 0. It doesn't go from 0, just 3 goes from 3 to 3, so it has no width other than 0. Okay, this is finding a function represented by a power series. Just kind of use geometric on this. Not too bad. So I'm using the geometric formula. You see n equals 0, and it's geometric, x plus 9 over 7 to the n. So I'm doing 1 over 1 minus x plus 9 to the 7th. X plus 9 divided by 7, excuse me, not to the 7th, divided by 7. And just get a common denominator, 7 over 7. And then that gives me negative x minus 2 over 7. That flips over to 7 over negative x minus 2, which is the same thing as pulling the negative out and leaving x plus 2. So same thing, and therefore it would be answer D. Okay. Let's look at the next one. Next one's a little trickier, because it's starting at 1 instead of 0. And that just means we'll do what I did earlier. We'll subtract the 0 term off of it. So we'll use that same formula. So I'm using 1 over 1 minus r. But I'm subtracting off the term of putting in 0 in here, which that'll just be 1. So on the bottom you have 1 over x minus 10, which will actually be 1 over negative x plus 11. Now this is, I didn't write that there, but obviously this is 1. So x minus 10 to the 0 is 1. So I'm getting a common denominator for 1, which in this case will be negative x plus 11. So 1 minus a minus x plus 11 gives you x minus 10 over negative x plus 11, so that's the correct answer. But to make it match the answers up here, I had to, you see it's x minus 10 on top, so we'll leave that alone, but I pulled a negative out of the denominator. If you pull a negative out of the denominator, that makes it x minus 11. Just stick the negative out to the outside, so it's answer C. But yeah, so it just had to rewrite it to make it look like the right answer. So that concludes this video for the sample problems for exam 3.